Okay, so in our last video, we looked at how to calculate chi-squared using our observed frequencies and calculating our expected frequencies. But how do we use that value to determine whether or not we should reject or fail to reject the null hypothesis? That question, or answering that question, begins with an assumption called the sampling distribution. A sampling distribution is a theoretical distribution made up from statistics gathered from an infinite number of samples. So what we're going to do here is we're going to assume that the null hypothesis is true and create a sampling distribution based on that assumption. In other words, if the null hypothesis is true and we were to calculate an infinite number of samples, most of the time we should get a difference between our observed frequency and our expected frequency of 0. Once again, that is, if the null hypothesis is true, we should observe a difference between our expected frequency and our observed frequency to be 0 most of the time. However, we know that due to sampling error, we might observe some differences that are greater than 0. But the magnitude of those differences should get smaller as we get further away from that 0 point. This is reflected in the chi-squared distribution that I've illustrated below. Here, the chi-squared distribution is a positive skew distribution with a mode of 0. As the figure illustrates, the larger the value of chi-squared, the fewer we should expect to see if we're randomly drawing from a distribution where we should actually be pulling zeros. So the fundamental question using the chi-squared distribution is, what is the likelihood of drawing our observed chi-squared value from this distribution if the null hypothesis is true? If the probability of drawing our observed chi-squared value is relatively low from this distribution, we might therefore have enough evidence to confidently reject this distribution and its underlying assumption that the null hypothesis is true. That is to say, if our observed chi-squared value is very different from what we would expect out of this distribution, then it's likely this distribution is not correct, as it did not produce the chi-squared value that we see in our sample. This line of thinking begs the question, though, what is the probability of drawing our observed chi-squared value from the chi-squared distribution? That is, if the chi-squared distribution represents the null hypothesis, what is the likelihood that we actually see our observed value by random chance or sampling error from this distribution? So going back to our thinking about probability, the probability the null hypothesis is true is the likelihood the observed chi-squared value was drawn from the chi-squared distribution. That is, the probability the null hypothesis is true is the likelihood that we observed our chi-squared value by random chance or through sampling error from a distribution that assumes the null hypothesis is true and is made up of mostly zeros. Using the rule of subtraction, we can further conclude that the likelihood or probability the null hypothesis is false, that is P not A, is 1 minus the probability the null hypothesis is true. So for instance, if we find that there's a likelihood of, let's say, 15% that our observed chi-squared value came from the chi-squared distribution, we could take 1 minus 15 for an 85% confidence level that the null hypothesis is false. So once again, we can use basically the probability that a value is drawn from a sampling distribution to give us some insights into the likelihood that that distribution is the way the world works and accurately characterizes our relationship between our two variables. So here, if the null hypothesis is true, that is, if the probability of the null hypothesis being true is less than or equal to 0.5%, then we conclude with 95% confidence that the chi-squared distribution is not the distribution our observed chi-squared value was drawn from. Thus, we can reject the null hypothesis that the relationship between x and y is 0 if the probability of drawing our sample statistic from the chi-squared distribution is less than or equal to 5%. So the more practical question is, how do we determine the probability the null hypothesis is true? That is, how do we determine the probability that our observed chi-squared value came from the chi-squared distribution with a mode of 0? There are two ways to do this. One, we can look up the probability in a probability density function table. Or we can use a computerized package like SPSS to compute the actual value of pH0. Let's take a look at how we calculate pH0 using a table first. So recall from our example in our last video that our observed value of chi-squared was 23.04. Our question then is, what is the probability of drawing a chi-squared value of 23.04 from the chi-squared distribution? So here I've reproduced the chi-squared distribution table along with the visualization of the chi-squared distribution. These chi-squared distribution tables may vary a little bit from textbook to textbook, but all have the same general information. In most of these instances, what we're trying to figure out is the critical value that is associated with the confidence level we're interested in. When I say critical value, I mean at what value of chi-squared do we see 5%, in our case for statistical significance, of the observations in the right-hand side of the tail and 95% to the left-hand side of that particular value. So to use this table, you need to first match up your single value from your rows and your columns. You'll see here that the rows are defined by what are called degrees of freedom. Degrees of freedom are calculated by taking your number of rows minus 1 times your number of columns minus 1. Basically, what the degrees of freedom does is it penalizes the probability based on the size of the table, because we know that larger tables will automatically have higher chi-squared values. So here we know in our example from the last video that we had 2 rows and 2 columns. Our 2 rows reflected our party ID of Democrat and Republican, and our 2 columns reflected our gender of male and female. So 2 rows minus 1 gives us 1, times 2 columns minus 1, which is also 1, so we have 1 degree of freedom. As we mentioned earlier, we're interested in the 95% confidence level, or if we subtract 9.95 from 1, the 0.05 level. So here we want the probability of our value, that is our probability of being in that shaded yellow area, to be 0.05. So we have our degrees of freedom 1 and our desired confidence level of 0.05. We simply then need to match up our row and our column to find the value of chi-squared that defines that point on the axis. So you can see here with some highlighting, I've highlighted the first row and the 0.05 column. That gives us a critical value of 3.84. The critical value is the value of chi-squared where the area to the right is equal to the confidence level. I've illustrated this on the figure on the left-hand side. So you can see here that when the chi-squared value is equal to 3.84 with 1 degree of freedom, 95% of observations fall to the left-hand side of that chi-squared value, and 5% of observations fall to the right of that chi-squared value. What this basically means is that this is the value of chi-squared you need to hit in order to achieve a 95% confidence level, or in this case, a 5% chance that the null hypothesis is true. So here we see that our value of 23.04 greatly exceeds our chi-squared value of 3.84. That means the probability of drawing a 23.04 from the chi-squared distribution is going to be much less than 5%. So, in this case, or any case where the observed chi-squared value exceeds the critical value from the table, we would say the result is statistically significant at the stated confidence level. You can, of course, pick different confidence levels and get different values by picking different columns in the table. Let's say you wanted to look at the 90% confidence level. You can move over to the column to the left of our 0.05, and that gives you a value of 2.71, which means that if you hit 2.71 or higher, you're at the 90% confidence level. Similarly, if you have a bigger table, let's say you had a 4x4 table, that would give you 2 degrees of freedom. You would pick a different critical value that you would need to exceed to make sure your results are statistically significant. All right, so here we're going to demo how we get chi-squared in SPSS. So I have the SPSS browser open. I'm going to import some Excel data that I've already created that kind of go along with the example we were using earlier in the video. Okay, so here we have our data open. I've got observations, OBS, which is simply a number from 1 to 100. So as you can see, there are 100 observations in our sample. Gender is a variable coded F for female and M for male. And then I have 3 party variables to demonstrate the different types of chi-squared values we can get depending on how much that variable differs from our observation. So party underscore OBS is our data that we used earlier in the video. We had 37 and 13 for the parties and the gender. Party 0 chi-squared is pretty much the same data that you would get from the expectation if the null hypothesis were true. So we've got 25 male Republicans, 25 female Republicans, 25 male Democrats, 25 female Democrats. We should expect with party 0 chi a chi-squared value of 0 when we calculate the value. And then finally, I've got party underscore no REL. This is a variable where I've slightly modified the party 0 chi variable to include a few Democrats, more Democrats on the female side, and a few more Democrats on the male side. But it's not enough deviation that we'd expect it to be statistically significantly different than our expectation of the null hypothesis. So in order to actually test chi-squared, it's quite simple. we're going to go up to our Analyze menu under Descriptive Statistics and Crosstabs. And here, just like we did before with making crosstabs, we're going to put our independent variable in the columns, and we're going to put our dependent variable in the rows. So gender is our independent variable, and here, just to illustrate, let me do party 0 chi first. This is where, once again, we have 25. You can see here in our chi-squared table that Pearson's chi-squared for its value is actually 0.000. That's because our crosstab for party 0 chi is no different than our table generated under the null hypothesis. You'll see here that since we have a 2 by 2 table, we have 1 degree of freedom, 2 minus 1 times 2 minus 1. And because the chi-squared value is 0.000, we are 100% certain that the null hypothesis is true, so we get a significance level of 1.0. Keep in mind that for statistical significance, we're looking for the null hypothesis to have a probability of 5% of less being true. So we want this answer to be 0.05 or smaller to reject the null hypothesis, include that a relationship exists between our independent and dependent variables. Let's kind of go back and do the same thing. Here, I'll do the party-no relationship just so you can see how even slightly changed it still gives us a non-statistically significant relationship. So I'm back to Analyze, Descriptives, Crosstabs. I'm going to swap out my variable for party-no relationship. Chi-squared is still checked. I click OK, and I have my new results. So here you can see I've modified the table slightly. I've got 29 female Democrats, 21 female Republicans, 21 male Democrats, and 29 male Republicans. The totals are still the same at 50 Democrats, 50 Republicans, and 50 males and 50 females. Now you can see here down in my chi-squared test, because there's some deviation in this box, I can actually calculate the difference, which SPSS does for me, between our table and the null hypothesis table, which had 25 in each cell entries. Obviously, we don't need to go through the math ourselves. SPSS calculates that value to be 2.560. And in this case, we still have 1 degree of freedom, and we're getting our significance level, or our probability that the null hypothesis is true. So here SPSS is telling us that the probability that the null hypothesis is true is 0.11, or about 11%. The null hypothesis needs to be 0.05 or less to be statistically significant. So in this case, we would fail to reject the null hypothesis because we're only 89% confident that the null hypothesis is false. Or in other words, we're 11% confident the null hypothesis is true. So keep in mind that SPSS produces the results a little bit differently. You can always think of the significance level as the probability the null hypothesis is true. And since we want the probability of the null hypothesis being true to be 0.05 or less, in this case, the results are not statistically significant. Finally, let's go back and look at our observed variable, or our observed values that we had earlier in our video. Once again, I'm going to go back to crosstabs and put that value in, which is party OBS for party observed. Here you can see that I've got the crosstabs that we had earlier, 37 female Democrats, 13 female Republicans, 13 male Democrats, and 37 male Republicans. Here, once again, SPSS calculates our chi-squared value for us. It's 23.04, which is what we got by our hand calculation earlier in the video, and we still have 1 degree of freedom. Now here you'll see with such a high value, 23.04, our significance level is 0.000. It doesn't really mean that it's 0, it just means that it's smaller than the 3 decimal places. So once again, we're looking for that value of the significance level to be less than 0.05, meaning that we want the probability of the null hypothesis being true to be 5% or less. In this case, 0.000 is clearly below the 0.05 threshold, so we would take this to mean that we can confidently reject the null hypothesis at a greater than 95% confidence level and conclude that there probably is a relationship between gender and party ID as we observe in our sample data.